Welcome to Chapter 4 in Payment Management System class, and in this chapter we will be talking about the payment performance, especially the structural versus functional performance. So the question here is, what's the difference between functional versus structural performance? If there is a difference in the way we measure it, if there is a difference in the impact that it's gonna make on the maintenance and reconstruction activities. This is what we're gonna learn during this chapter. So let's start with functional performance. What do we mean by functional performance? It's basically a user perception on the serviceability and safety of the road. It's and so many times the way we measure how good is the road or how functional the road is based on the ride quality. For example, roughness. Sometimes we drive on a road and we say that road was really rough versus a road that was kind of smooth. The other parameter that we typically use as a factor to measure the functional performance is skid resistance. And the question here is, was the driving on certain street, was it safe, or did you feel that the car or the tires were really skidding on the surface of the pavement? So here is an example of two different pavement performances from the functional perspective. We have a very rough road here. As you could see, there's lots of cracks. Besides cracks, we also have the surface, the texture of the surface is really rough, and typically this is an indication that the road is rough and we need to think of something to improve its smoothness to reach what we see in the other picture here. And this is a good example of a smooth pavement where you're gonna drive on it safely, and at the same time even the fuel consumption driving on a smooth pavement is gonna be significantly lower than driving on a rough pavement. How about now the structural performance? So the structural performance is really the capability of the pavement to withstand the combined action of traffic as well as environment. We all know that the pavement has to interact with lots of traffic loads, but not even that. We also typically deal with different types of weather conditions. So I may have, for example, a shoulder on a highway that doesn't deal with any much of traffic but still fails, or we see some thermal cracking. So what's the reason here? Again, it's the environment. So those two reasons, traffic as well as environment, typically they would generate several types of distresses. For example, we're going to see surface cracking. Surface cracking can be again thermal cracking as well as reflective cracking and fatigue cracking. We also can see surface defects. Also, we can expect to see rutting and shoving, potholes. We can see also patch deterioration. So there was a pothole, we come back and try to patch it, and over the time that patch wasn't done right, or the serviceability or the life of that patch is over, and now we see the patch is deteriorating. Also, we can see as part of the distresses the construction deficiencies. For example, there are some spots we didn't compact it very well, or the mix was too cold while compacting it, and that's gonna come up with, or that's gonna cause extra distresses on the road. We also can see the loss of support. Loss of support is one of the major reasons for starting most of the distresses, which is basically happens at the soil or the base and the sub-base layers. So once we lose the strength that's coming from the underneath layers, then the entire pavement will be affected and the overall structural performance are going to be lowered. One of the major problems when it comes to structural performance is alligator cracking or fatigue cracking. We already talked about this in the previous chapters, but just to give you a reminder, the fatigue cracking, it really starts from the bottom of the hot mix asphalt layer, and then by the repetition of the traffic loads we're gonna reach the maximum tensile stress that the pavement can take in tension, and then the crack is gonna initiate from the bottom of the hot mix asphalt layer until it reaches the surface. Once it reaches to the surface, that's an indication for us that the entire hot mix asphalt layer is cracked, and there's not much really to do here. The cracks are gonna typically start from the wheel path and then start to connect, as you could see here, until we see that alligator type of cracking. This is here another example of structural failure. Basically, we can see a block cracking in Portland cement concrete pavement. So we talked about this already, that block cracking can happen in hot mix asphalt as well as Portland cement concrete. And as you can see, the way we call it block cracking, because the cracks now are forming more or less blocks. They start with bigger area of blocks. Typically it starts with a longitudinal cracking and some thermal cracking, and then they start to interconnect, and then they would form those little blocks. This is here another example of the structural failure that we see in hot mix asphalt. It's raveling basically with the presence of drainage problem. The water now is interacting with aggregates and the asphalt, and eventually it's gonna disintegrate the relationship between aggregate and the asphalt, and as a result we will lose the mixture, as you could see here, and now the entire structure is failing. This is an extra example of a structural failure due to environment rather than loads or traffic loading. This is the low temperature cracking that happens in hot mix asphalt. It's typically, the way you can recognize it, it's 90 degrees perpendicular to the traffic direction, and as I said, it's not really related to traffic loading. It's mainly related to either a very low temperature night, from just one night. If we reach very low temperature, that it's gonna lead to very high induced tensile strains in the pavement layer, then the thermal cracking will initiate. Or it can happen during a full winter season, when we see a huge difference in temperature between daytime and nighttime, and that will be also the result, as you can see here, a low temperature thermal cracking. So after we're done here with some examples of structural versus functional performance, now the way to interact and use the stresses data into the pavement management system is, as you could see in this table. So the very first column here, we need to identify what's the distress. Is it a crack? This is the category of the distress. Is it a type of cracking, or surface defects, or all the way to loss of support? And then here we need now to be specific what type of distress. For example, under cracking, you can see you may have alligator fatigue cracking, block cracking, edge and longitudinal cracking, all the way to reflective cracking and joints at joints. And another example here, we can see surface disconfiguration. Surface disintegration. Here we have the example of potholes, and all the way to loss of support. Specific distresses based on loss of support are the water bleeding and pumping. We can also have expansive soils that's gonna eventually result in differential movements because of the frost heaving soils, all the way to differential movements as a simple specific distress. Then once we specify exactly what type of distress and under what category, then we will move on to at what layer does this crack start at. Does it start at the surface, or at the base, or at the sub-base, or even at the subgrade? So for example, let's see here block cracking. For example, block cracking, we can see block cracking starting or originating at the surface, or at the base, or it can be even at the sub-base. Typically it doesn't really start with the subgrade. Now if we take another example, the surface disintegration, which is the potholes, the one that we talked about, the only layer of origin for potholes would be the surface only. Going all the way now to the loss of support, if we have water bleeding and pumping, this happens mainly starts at the base layer and then it propagates all the way to the surface. While if I have expansive soil differential, then this means it definitely has to start from the subgrade where the soil is, or the expansive soil is, and then it starts to affect the entire structure. Then the fourth major column would be the presumed diagnostic cause. What's the cause? Is it because of loading, weather, materials, or construction? So, for example, if we look at the alligator cracking, the major cause of having fatigue cracking is mainly loading. It's repetitive traffic loading over time. We're gonna reach certain limit beyond which the pavement cannot take any more tensile stresses, and therefore the alligator crack is gonna initiate from the bottom of the hot mix asphalt layer and it's gonna go all the way up to the surface until we see it. When it comes to block cracking, now it's a combination between weather as well as materials problem. And let's talk about surface disintegration, potholes. Again, if you go all the way to here, the major reason here is now loading as well as weather. The very first thing is definitely loading, because we're gonna have a repetitive loading on certain point that is kind of weak. So this is the way it's gonna initiate. And then the weather, well, what I mean by weather here, it can be temperature or water. In this case, for potholes, it's mainly water. It's gonna let the water in, and this is where we see the disintegration between aggregate and the asphalt. All the way to the loss of support. Again, if we pick on the expansive soils, it's mainly because of weather. Again, the water is gonna get into the system, it's gonna make its own way to the soil. Once we get to the soil is gonna expand and it's gonna make the entire structure fails. And here, definitely, if we have any comment, we will be definitely putting it here. Is it related to, for example, DM here means it's still related to material and design as well. Here another table that shows you the same thing: distress category, specific distress, layer of origin, and what's the diagnostic cause, as well as comments. But this time now it's for jointed Portland cement concrete pavements. So, for example, if we pick on, first of all, the distress categories, we have cracking, we have joint deterioration, we have surface defects, we have repair deterioration, construction deficiencies, all the way to loss of support. And then under cracking, we may see four types. We may have corner breaks, we may have durability or decracking, longitudinal cracking, all the way to transverse cracking. For example, if we look at loss of support, we can have again water bleeding and pumping, expansive soil, frost heave, and differential movements. When it comes to soil or the loss of support, it's pretty much similar to the hot mix asphalt. How about surface defects? Surface defects can be map cracking and scaling. It can be polished aggregate or pop outs. And then we can see here, this is the layer of origin. It's kind of interesting here that most of the cracks that is related to the PCC is really depending on the Portland cement concrete layer. Very minimal that you would see a sub-base related issue or a subgrade. The only thing that's really related to the subgrade would be the loss of support. But mainly, it's all depend on the top layer of Portland cement concrete. When it comes to the diagnostic cause, it can be again load, weather, materials, or construction. And again, they vary. It depends on the type of cracking or depends on the type of loss of support, for example. And then we have the last column, definitely, to explain whether it's coming from design or materials. Here we have a very similar example. I'm not going to go through the details here because now it looks similar, but I need to mention that this table now is for continuously reinforced Portland cement concrete. But as you see, it's the same. We have to distinguish the distress category, the specific distress, what's the layer of origin, and then what's the diagnostic cause for the problem. Now the question comes here is, are the functional as well as the structural performances, are they related to each other or not? And the question is yes, they are pretty much related. For example, ride quality, which is a very functional performance property, is really impacted by the cracking, several types of cracking, as well as potholes and shoving. If I don't have fatigue cracking or thermal cracking, or the potholes are very seldom, and I don't have any shoving problem, then the ride quality would be good, and therefore the functional performance would be good. So that tells you here an example that yes, they might be in several cases related to each other, functional versus structural performances. This relationship also can be the other way around. The functional performance, for example, a rough road, can and would generate a very high dynamic loads, which eventually could lead to a structural distress. So previously we showed that yes, the structural performance can affect the functional performance. Here is vice versa. Therefore, really the occurrence of structural deficiencies would result in poor functional performance and vice versa. Okay, so now we have a good introductory information about both functional versus structural performance. So let's now talk more about the functional performance of pavements. The very first parameter that is used to judge the functional performance of pavements is roughness. So how do I define roughness? Roughness is typically refers to the deviation of the stress from a true planar surface with characteristic dimensions that really can affect the vehicle dynamics, the ride quality, the dynamic loads, all the way to drainage. So the question is here, looking at these two pictures, you can tell there is one is rough, which is this one, and this road here is very smooth. And if I ask any driver and ask, okay, how comfortable is this road to drive on, definitely he or she are not going to be happy to drive on that road compared to this one, which is pretty smooth, and I'm going to have a ride comfort trying this one over this rough road. So pavement smoothness is an equal effect, and it has an equal meaning of ride comfort. So when it comes to ride comfort really depends on, first of all, human response to vibration, then the vehicle response to the road, all the way to the road roughness. So the very first one, which is human response to vibration, sometimes again, if you are young versus a bit older, your response to the vibration is going to be different, and therefore your ride comfort is different. Same thing for vehicle responses. If I have an old car, the way it's going to react to the road roughness is going to be totally different than a brand new car, which is you're not going to feel it that much, and the vehicle response, it's going to deal with a rough road in a much nicer and smoother way compared to an older car. And then our factor that we can work on from the engineering perspective is really the road roughness, and how can we improve the roughness of the road itself. Therefore, if roughness is really important for us, so how can we measure roughness? So the way we measure roughness, we have to think of the pavement profile, and then how can we measure the response of the vehicle to the pavement roughness, as well as the pavement profile has to be eventually converted into a measure of roughness, and then the vehicle response must be also calibrated to a common reference. The question now is, if roughness is important and we need to think of measuring it, then if there are indices out there that we can use to measure roughness in a standardized way. So there are three major indices and indicators to measure pavement roughness. The first and foremost famous one that most of highway agencies use nowadays is the International Roughness Index, which is IRI. Also, sometimes we use root mean square vertical acceleration, all the way to an older way of measuring roughness, which is the slope variance. So as a preliminary stage here, we need to define what's pavement profile. So pavement profile, as you could see here, it's a plot of elevation in the y-axis versus the longitudinal distance along the pavement. So the profile alone doesn't really mean a lot to pavement engineers, but we will be using it to define roughness. For example, eventually we are gonna look at the elevation for this point versus the elevation of the adjacent point all the way to here, and the difference in elevation and the pavement profile will give us an indication how rough or smooth that road is. This is here a true example of the importance of pavement profile and how does it give us an indication of the pavement roughness. For example, this particular section of pavement really identifies a bump that has been causing one of the several pilots to complain during takeoffs. So as you could see here, imagine now this is the runway, and now the pilots are really trying to take off, and all of a sudden there is that abrupt change into the elevation. You are gonna ask me how much is that change? That change, if you can see, the average here is 0 elevation, and once you reach this peak here, it's 2 inches. Imagine a plane that is in a very high speed about to take off, and now the tires are gonna deal with this abrupt change, significant change in elevation, even if it's just 2 inches, but that 2 inches with a very high speed, it will generate a very significant bump that pilots kept complaining about. And yes, when we send technicians to the field, to the runway, yes, they were able to capture that by simply having the pavement profile, which is elevation versus the distance. So what is the International Roughness Index, or the IRI? Basically, the IRI is nothing but a mathematical representation of the accumulated suspension stroke of certain vehicle, and then we divide that accumulated suspension by the distance traveled by the vehicle during a test. And then instead of the calculation of the suspension stroke with a test vehicle, in order to estimate the vehicle acceleration, which is experienced typically by a body traveling at constant horizontal velocity along the road profile, such as the RT-RRM devices, which I'm going to explain later on. Now the IRI system is calculated from a measured longitudinal road profile by the use of QCS. And what is QCS? We're gonna learn this in the next slides. So now this is here is gonna give you an understanding what do I mean by QCS, which is, as you could see here, is quarter car simulation. This is the way the IRI, which is the International Roughness Index, was originally measured. So the IRI is typically obtained by performing a quarter car simulation on longitudinal profile, and then this is performed typically at 50 miles per hour, and there is an ASTM standard which is E1926, which is documenting the overall computational procedure on how to measure the IRI from the mathematical perspective. So as you can see, it's just 1/4, which is basically this system here is we put it on one tire out of 4. We measure the profile using this mechanism here. As we could see, we have the load mass, we have a spring, we have a suspension, spring and damper, all the way to the tire spring. This information is going to go through a computational algorithm, which is eventually going to lead to us of a good estimation of the International Roughness Index. So as I mentioned before, one of the major reasons for coming up with the IRI index is really to provide the pavement community with a very common roughness rating for pavement worldwide. And the way we measure IRI is basically from a mathematical model that simulates the vehicle suspension response to roughness. And again, as I said before, why we say quarter car simulation, because simply we are referring to a quarter car simulation, since it represents the roughness response created by one single wheel of a typical passenger car. So the QCS model, or the quarter car simulation model, it represents and it has a sprung mass of vehicle body, which is MS, and then this is here the sprung mass, and then also we have a suspension, which is including a spring plus damper. So the spring here has the coefficient Ks and the damper has Cs, and then we have the unsprung mass, which is Mu, and then all the way to reach the surface where we have now the tire or wheel assembly, and that's here the tire spring KT. Once we have all those parameters defined, now I'm really interested to measure three different types of elevations or point of interest. The very first one is Z. Z is simply the road profile elevation points, which is the interaction between the tire and the surface of the pavement. And then also I have ZU, that's the elevation of the unsprung mass, or the axle. The axle is going to keep changing up and down based on the roughness of the road, and my interest is to measure that as well. All the way to measure the overall elevation of the sprung mass. Now I want to measure the entire difference in elevation of the entire axle or the entire tire. Once I measure all those different points, now the difference between the elevation of the body of the car, which is ZS, and the axle, which is ZU, in response to the road profile and vehicle speed, is the integral of the difference in velocities between the sprung compared to the unsprung mass. So if we do a little bit of integration here, and how can we come up with a mathematical model, QCS, which is the quarter car statistics, is simply 1 over C. See here, this is the length of the section. Now we're gonna have an integration from 0 to T, this is the time, and then we're interested to see the difference between ZS minus ZU over time, and this is how we measure the International Roughness Index. So the World Bank recommends the use of the following parameters to measure and have a good estimate of the International Roughness Index. For example, KT over MS is 653 second to the power minus 2, and then we have KS over MS, we have this much, all the way to MU over MS, which is 0.15. This is here a unitless value, but MS is 100 kilograms and MU is 15 kilograms. And all this is going to be now termed the QCS as the International Roughness Index. This is here a table that shows you the vehicle parameters that is used to measure the International Roughness Index. First of all, we could see here the parameters that we would end up using and what's the unit for each one of those parameters. Now we have different vehicles here. So we have competition, compact, mid-size, full-size, all the way to small truck. The one that was used originally as the QCS 1/4 golden car was the full-size car, and those are the numbers that they used as preliminary numbers to measure the International Roughness Index. So the question now is, based on all those parameters, we're going to come up with one single number, which is IRI, and the unit for the IRI is typically inch per mile, and there are some recommendations how to classify pavements based on their performance from the IRI perspective. So these are some general guidelines to give you an idea how smooth or rough is the road. So if the IRI, the measured IRI, is somewhere between 0 and 80 inches per mile, this is a good indication that this road is super smooth. While If the IRI is somewhere between 81 and 130 inch per mile, this is a medium roughness. Once I hit that number, typically it's 130 inch per mile, now I have to consider that this pavement is really rough now. So now once we got to know some of the indices that used to measure roughness, the question now is, what are the devices, engineering devices, that we use to measure pavement profile in the field? So we're going to go through several types of devices, from the simplest one, which is the phase dipstick, all the way to high-speed road profiler, and now we're even using the inertial profilometer. And then we're going to also try to discuss a little bit the response type devices. So the very first one here, which is still existing roughness device that is used by some small highway agencies, is the phase dipstick. The phase dipstick, as you can see here from the picture, it's really consisting of an inclinometer. What is inclinometer? Is really measure the difference in elevation between 2 points. I have 1 point here and 1 point here. I'm gonna have more illustration in the next slide, but simply we have that inclinometer that is enclosed in a case supported by 2 legs, and it's separated by 12 inches. Those 2 digital displays are provided, one at each end of the instrument. So I'm really interested to know the elevation of point A versus point B, and this is what's gonna give me an indication of the road profile and therefore a roughness index. So each display is gonna read the elevation of the leg and its end relative to the elevation of the other leg. So this is what I'm talking about here. I have point 1, I have point 2, and the distance between these 2 points is 12 inches. And we're going to measure again the difference in elevation between point A or point 1 and point 2. Once we get the distance between the feet, the 1 feet distance, this now can be adjusted to other than 12 inches. Feet are interchanged by rotating the entire equipment by 180 degrees to come up with a replicate information. So we don't depend on one data per section. We would measure it and then we will flip these two together and measure it again and then come up with an averaged value. So once we come up with the differences in elevation between several points, then we can use it to construct road profile and eventually calculate either SV, which is slope variance, or the International Roughness Index. But the issue here, the production rate is not that much. It's about 900 feet per hour, and it's highly used for calibration purposes only. Why? Because it is very accurate, but at the same time it's slow, and that's why here I put the advantages versus the disadvantages for the phase dipstick. The advantage is, again, it's low initial cost. It's just $29,000 roughly, but it's very precise as well. When it comes to disadvantages, again, slow speed. We cannot really use it that much, especially when it comes to a bigger network, and we need to close off the facility when we do such measurement, rather than other types of measurements that we tend to not to close the road, which simply is going to be a vehicle driving at the speed limit. So speaking of other high-speed road profilers rather than the phase dipstick, we have here the TRRL profilometer. Basically, this machine was developed by the Transport and Road Research Laboratory of England. That was in the mid-1970s. Basically, this device, as you could see here, at the beginning of the test, it sets some initial measurements to establish some data, and then once now we start in using the machine, now the road elevation at the leading sensor compared to the other recorded by other sensors as the trailer moves would be now producing a continuous profile. Those laser signals would really be produced now to cancel any beam motions. So as you could see here, we have, those are the sensors, that they are measuring distances, laser sensors, and here we are measuring the horizontal distance measurement instrument. The vehicle again can really travel at normal speed on highways. There are 4 lasers as are used to measure distance between the sensor and the pavement surface continuously. So here let's take a closer look at the inertial profilometer from the inside. As you could see here, first of all we have at the back tire here we're measuring a longitudinal distance using odometer. At the same time we're having here a measuring probe. It's a non-contact distance measuring probe, either laser, ultrasonic, or infrared. This is basically we're trying to measure the distance between the vehicle and the road surface. Then the waves are gonna go hit the road surface and then reflect back and measured by the accelerometer, which is eventually now this is a device to compensate for vertical movement of vehicle body. Once you do this, then you will be able now to calculate the road elevation, which is dP plus dV. And definitely you have to have a computer system to measure all the data responses and eventually come up with a road elevation profile. So as I mentioned before, simply the accelerometer here will be used to measure the vertical movement of the vehicle, which is dV, and therefore the road elevation would be dP plus dV. So in a nutshell here, the distance measuring probe and the accelerometer must be synchronized very effectively in time domain to have a very accurate results. Otherwise the results has to be calibrated. So again, the road profile can be measured at a relatively high speed, which is a big advantage compared to phase dipsticks and other conventional measurements devices. But we need to keep in mind that the higher the speed, the longer sampling distance, and also minimum required sampling distance typically is 1 foot. One of the disadvantages though is the cost. The cost of the machine to buy it and keep maintaining it is somewhere between $300,000 to $500,000. This is here another example of inertial profilometer, which is called ARAN, which is used now pretty heavily in Canada. It's used by the Roadway or the Roadwear Corporation of Ontario, Canada. Basically the machine here has 2 major components. The in front component here, as you could see, there is a laser support beam accelerometer, and at the back tire here you see the distance transducer. It's similar concept, and eventually we are interested to measure the road profile. Another example here of inertial profilometer, which is used in South Dakota DOT. It's named as South Dakota Road Profiler. Simply at the front of the vehicle you could see here there are 3 ultrasonic sensors as well as 2 accelerometers on the front bumper. Basically it's the same concept, trying to measure the distance from the vehicle body to the pavement surface, but there are some research results that show that there are some problems with obtaining reliable measurements, especially when it comes to coarse textures pavement, because now we're really going to deal with the roughness on a smaller scale in pavement rather than the overall profile change between point A and point B. So in summary, this is I tried to put most of the roughness data collection equipment together. This is from a report that was published by FHWA in 1989. It's still applicable. We have several roughness data collection devices, from dipstick, profilographs, all the way to non-contact profiling devices, and then second column here would include what's the major principle of the measurement. For example, dipstick is using a simple direct differential measurements between point A and point B. while some other devices such as again the non-contact profiling device is using direct profile coordination. And the relative initial cost typically with dipsticks is the lowest cost. The profiler graphs all the way now, once we hit for example South Dakota profilometer, it's kind of medium, and then once you have profiling devices that use again accelerometers and laser waves, the cost is going to be pretty high. But on the other side, the data collection cost is again sometimes is low when it comes to higher speed machines like here, because again the initial cost was high, but the return is now the cost of measuring the data is really low, really low compared to dipstick. Is really impractical to use it for high amount of data collection. The degree of accuracy, even now most of the machines are very accurate. Dipstick of course is very high accuracy. Profilographs is kind of medium, but now the new profilers, they are very accurate machines. Most of those devices were developed in the 70s and the 80s, but there is several improvements over the years have been done, especially on the profilographs and the profiling devices. The extent or current use, again dipstick is not used that much for a limited case, especially when it comes to calibration, while for example maze meter or other profile meters now is used extensively. When it comes to the projected extent of the use in the future, again it's pretty much the same. For dipstick, it's not used that much now on a daily measurements. It's mainly just for calibration, while other profilographs there is an significant increase use every year. So now let's shift gears and talk a little bit more about the roughness data collection guidelines. For example, if I'm outside and I'm measuring now the International Roughness Index or any roughness indices, how and what should I think of while I'm in the field that may affect my roughness readings? First of all, we need to remember that typically when we measure roughness, we depend on the outside travel lane, if possible, which is the right lane, just because this is the worst case scenario where lots of big trucks are traveling on that lane, and it will be critical to measure roughness at that lane. Also, we need to keep in mind the weather condition while we're measuring roughness. For example, temperature has to be somewhere between 40 and 100. If you are really going at a snowy day, that's not the best day to do it. Or if it's at very high temperature, let's say 120 degrees in the middle of the summer in Phoenix, Arizona, that's also not a good selection, because now the binder is really start to flow or may flow, and it's gonna definitely change the roughness of the road at that day in particular. Data collection also shouldn't be performed when there is any abrupt change in the weather. If there is a trend that the temperature at this time of the year is around 50 degrees, and at that day for in particular was 32 or lower, then you wouldn't measure the roughness readings at that day. Also, the speed that we measure the roughness at is very important. So data should be collected at speeds within the recommended range. If the initial or if the speed limit at certain street is 45 miles per hour, you should be measuring roughness around that speed, not at 20 miles per hour or not at 70 miles per hour, because it will affect the reading. So we have really to keep maintaining the speed constant over the entire section. Also, there are some significant impacts on bridges or railway crossings and those crossings or intersections should be excluded because they will not be giving us representative values for roughness. Also, the amount of loads will affect the roughness readings. So dynamic load varies along the road, which typically will generate different pavement responses. So here is in a summary some of the factors that affect the dynamic forces distribution and what are the possibilities of having this factor. For example, truck configuration, the possibilities is we may have single unit, tractor, or trailer, and each one of those are gonna experience the road roughness in a different way. We also have suspension type. We may have spring leaf, walking beam, all the way to air suspension. Even the tire type. We have bias, radial, dual, and single. Even tire pressure can be low or high, and once you change the tire pressure, it will significantly change and affect the roughness experience. Also the speed, if it's low versus high, that's also going to affect the roughness. Another factor that can affect the pavement roughness is the pavement material itself. So if I'm changing the property of the materials along the longitudinal distance, this may result in variation in pavement response, and therefore is going to change the measured roughness of the road. For example, if I have if I'm experiencing a lot of high severity faulting and jointed Portland semi-concrete pavements, then this will affect the roughness measurements. This is gonna have now a longer wavelength, and therefore the roughness measurements is gonna be not accurate. Environmental factors. For example, if I have a frost heave or swelling soils or poor drainage, all those will definitely affect the roughness measurements as well, and I need to be aware of it before I go to the field and take representative roughness measurements. The remaining question here regarding roughness, after we got to know how to measure it and what are the devices to use it and what are the conditions to be aware of while measuring roughness, is now how can we fix it? So, and what are the typical maintenance and rehabilitation activities for solving roughness problems? First of all, we need to remember that roughness is mainly affecting the functional performance of the pavement. Therefore, the entire structure, I'm assuming it's well and it's very healthy. The only thing that I need to worry about is the top 1 or 2 inches, and that's why the major fixation for roughness is really to have a functional overlay, and that overlay is going to be about 1.5 to 2 inches. Sometimes also we do a mill and fill job if we have the chance to do so. So when it comes to flexible pavements, we're going to mill the entire surface, mix it with old materials as well as new materials, and repave it again. While when it comes to PCC, we typically try to restore the joints and establish a good connection between 2 adjacent beams. With that, we finish this part of the chapter regarding roughness, how we measure it, and how can we fix it in the field. Next time we will be talking about how we measure rutting as well as the skid resistance. Thank you.